Quantum mechanics reveals a fascinating truth. Objects can behave as both particles and waves. This principle, known as wave-particle duality, means that quantum objects, like electrons and photons, can exhibit properties of both waves and particles. The famous double-slit experiment dramatically demonstrates this strange behavior. In this experiment, we send particles like electrons through two narrow slits. When we observe which slit each particle goes through, they behave like discrete particles. Each particle goes through only one slit and creates a pattern of two bands on the screen. But when we don't observe the particles, something incredible happens. They create an interference pattern, as if each particle goes through both slits simultaneously and interferes with itself, just like a wave would. This bizarre behavior is explained by quantum states and the principle of superposition. In quantum mechanics, particles exist in what we call quantum states. But unlike everyday objects, quantum systems can exist in multiple states simultaneously. This is called superposition. Instead of being simply up or down, a quantum system can be in a superposition of both states at once. When we measure or observe a quantum system, this superposition collapses into just one of the possible states. Perhaps the most famous illustration of quantum superposition is Schrödinger's cat thought experiment. Schrödinger imagined a cat in a sealed box with a radioactive atom and a vial of poison. If the atom decays, it triggers a mechanism that releases the poison, killing the cat. But according to quantum mechanics, until the box is opened and observed, the atom exists in a superposition of decayed and not decayed states. This means the cat itself exists in a superposition of both alive and dead states simultaneously, until someone opens the box to observe it. Although this contradicts our everyday classical experience, the principles of wave-particle duality and superposition have been repeatedly verified by experiments. Heisenberg's uncertainty principle is one of the most profound concepts in quantum mechanics. The principle states that certain pairs of physical properties, like position and momentum, cannot be precisely measured simultaneously. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. If we measure position very precisely, making the position uncertainty small, the momentum becomes highly uncertain, with a wide range of possible values. Conversely, if we measure momentum precisely, we lose information about the particle's exact position. Mathematically, the uncertainty principle is expressed as delta x times delta p is greater than or equal to h bar divided by 2. Delta x represents the uncertainty in position measurement. Delta p is the uncertainty in momentum. And h bar is the reduced Planck constant, a fundamental constant of nature. It's crucial to understand that the uncertainty principle is not just a limitation of our measuring instruments. It's a fundamental property of quantum systems themselves. Now let's discuss quantum measurement and its profound implications. Before measurement, a quantum system exists in a superposition of multiple possible states. When we perform a measurement on this system, the wave function collapses, and the system assumes one definite state from among all possibilities. Quantum measurement has several profound implications. Measurements yield only one outcome from many possibilities. Results are inherently probabilistic. The measurement itself changes the quantum state, and repeated identical measurements might give different results. These principles of uncertainty in measurement form the foundation of quantum mechanics, leading to revolutionary technologies. Quantum computing leverages superposition and entanglement to perform complex calculations that classical computers cannot efficiently handle. Quantum cryptography provides secure communication channels where any eavesdropping attempts can be detected due to measurement disturbance. And quantum sensors achieve unprecedented precision in measurements, approaching the fundamental limits imposed by the uncertainty principle. The uncertainty principle and quantum measurement aren't just theoretical curiosities. They form the foundation for a new generation of quantum technologies that are revolutionizing science and engineering.